well. So whenever you're ready, the stage is yours.
Right. Thank you very much for the introduction, and thank you to you and Antoine for the invitation to come and speak. As he said, my name is Jimmy Juno. I'm a graduate student at the University of Maryland. And so what I'm delighted to be talking with you all about today is some of my thesis work, which I've affectionately titled A Modal Alias-Free Discontinuous Galerkin Algorithm for Plasma Kinetic Equations. Essentially what I want to focus on is deriving novel discretizations of the kinetic equation and trying to apply them. And all of this work is done in collaboration with the Jekyll project at the Princeton Plasma Physics Lab, and I've highlighted a number of people that have really contributed to this work. Now, since this mini symposium is entitled Mathematical Challenges in Computational Plasma Physics, it's worth starting with what is a really big mathematical challenge, at least fundamentally, about a lot of plasma systems. Whether it's the heliosphere, an accretion disk, or the intercluster medium, a lot of plasmas, close to home, in space, everywhere, are weakly collisional. Their mean free paths are much, much larger than the plasma physical scales, things like gyro radius. And this means that fundamentally, the equation system that we should be looking at is not a fluid equation system, but the Vlasov-Maxwell system of equations, if we really want to understand the dynamics of these plasmas. So what I've shown here is the Vlasov-Maxwell system of equations in all of its glory. You have the Vlasov equation for any number of species, protons, electrons, impurities, you name it. And it's coupled to Maxwell's equations through velocity moments of the evolved quantity, the particle distribution function, which provides a statistical representation of the particles, essentially their probability for being in a particular position and velocity. Now, this equation system is nonlinear. And so we expect at some point we're going to require assistance from the computer to really understand the dynamics of this equation system. And herein lies the mathematical challenge. This equation system is notoriously difficult to numerically integrate because it's high dimensional, up to 6 dimensions, 3 spatial and 3 velocity plus time. And while we could take the traditional approach of discretizing the distribution function with macroparticles, a Monte Carlo-like approach, or if you prefer the particle and cell method, where the particles are advanced along characteristics, and then these particles are sampled to construct the distribution function, this approach suffers from counting rules. And this is a real travesty, because the particle distribution function is such a rich tapestry of the underlying physics of a collisionless or weakly collisional plasma. It's not just great for making pretty movies of phase space, such as the evolution of the two-string instability here. Really, just by inspection, if you have access to a high-fidelity representation of the distribution function, you can tell a lot about the dynamics of the plasma. To take just one example, there are plenty of energization processes, things like resonant processes such as Landau damping, that can be identified just by inspection, just by looking at the particle distribution function to really see what's going on. Not to mention the fact that we're getting ever higher resolution and higher cadence data from modern spacecraft missions, such as the magnetospheric multiscale mission shown here of a bow-shot crossing where they actually witnessed reconnection and were able to tell us about the electron distribution function through that magnetic reconnection site. So since this is such a hard numerical problem, we expect that we'll have to leverage really modern numerical methods to tackle it. And the one I choose in particular for this approach is the discontinuous Galerkin finite element method. Now, this approach has been tried by other groups to the kinetic equation. For example, there's a collection of papers by Cheng et al. In the early 2010s. And so there's really solid motivation for this approach. If you're not familiar with the discontinuous Galerkin method, I like to think about it as a natural generalization of finite volume methods. Because in a finite volume method, you take your domain and you divide it up into cells, some triangulation or tessellation, and you evolve a single quantity in each cell, the cell average. But why restrict yourself? You could think about evolving 2 pieces of information, a cell average and a cell slope, and thereby construct a piecewise linear representation of your solution. Or go even further, even higher order representations, such as a piecewise quadratic, etc., etc. In doing so, you would retain properties of the finite volume method, which you think are highly favorable, things like locality of data, which will ultimately allow you to minimize communication and scale your method on modern supercomputers. But you would gain properties of the finite element method, things like high order accuracy, because you're constructing a higher order representation of your solution inside a cell. So what does this actually look like for the Vlasov equation? Well, let's take a phase space mesh, which I call T. And remember, this is eventually a high-dimensional phase space mesh. It can be up to 6-dimensional. And I'm going to divide it into high-dimensional cells, which I call K sub j. The problem formulation is to find a discrete representation of the distribution function, which is a member of this space V, such that for every cell, this equation is satisfied, which is called the discrete weak form. And I've obtained this equation by multiplying the Vlasov equation by these test functions W and integrating the nonlinear term by parts. So that now, depending on your numerical methods background, there are pieces of this that might look very familiar. If you come from the continuous finite element world, this volume term here likely looks familiar, but we now have an additional piece, the finite volume part of it, where I now have a surface integral with this capital F hat here, a numerical flux function, which is ultimately going to give a prescription for how the distribution function is going to advect in my phase space term. To complete the picture, since it's a Galerkin method, I'm going to expand my distribution function in these same functions W, and I'm going to pick my space V to be the space of piecewise polynomials of some order P. I could pick other basis sets, and we've already heard talks of people using other basis sets that are more favorable to their problems. What I will ultimately find is that piecewise polynomials have some really nice properties in a discretization of the Vlasov equation. More on that in a moment. So I still need to specify what this numerical flux function is here, this capital F hat. And what I end up doing is that there's two pieces of the Vlasov equation. You have v dot grad f, sometimes called the streaming term, and then you have the advection of particles in velocity space due to acceleration, the E plus v cross b. Since I have a velocity grid, the v dot grad f part is actually somewhat simple, because I know that particles in the upper velocity half plane will move from left to right, and particles in the lower velocity half plane will move from right to left. So I can use upwind fluxes for this streaming component. For the acceleration, for how the particles will move in velocity space, I'm going to use what I call a relaxed global Lax-Friedrichs flux. So this is a Lax-Friedrichs flux because it has two pieces. I have an averaging term where I'm averaging the flux on either side of this surface, but then I also have a penalization term. I'm penalizing the size of the jumps to ultimately introduce a small amount of diffusion and control the jumps in the distribution function. And I pick this parameter tau based on something I already need, the maximum acceleration in the system, because I'm going to need this to ultimately take stable time steps. And I want to emphasize here that I've pulled this alpha plus out here in the averaging operator. You might think that this should be alpha plus F plus alpha minus F minus, but importantly, the phase space flux is continuous at the corresponding surface interfaces. What do I mean by this? I mean that if you look carefully at E plus V cross B, in fact, because the electric and magnetic fields do not depend on velocity space, at constant velocity surfaces, alpha is continuous. This is actually a consequence of Liouville's theorem. In fact, what we have is a discrete analog of Liouville's theorem. Phase space is incompressible, and phase space volume will be conserved. Just to sort of briefly go over what we do for Maxwell's equations, we're also going to use dg, and the point of emphasis here is that I've changed notation for very good reason. As I've said, the electric and magnetic fields do not depend on velocity space. So now this new notation, changing from k sub j to capital omega sub j, and w to phi, is to emphasize that this dg representation is only in configuration space, only in x, y, and z. I still need numerical flux functions for the electric and magnetic fields, and I have a couple of possibilities that we've implemented in my code. One is central fluxes. We're just going to average the electric and magnetic fields on each side of the surface. And the other is upwind fluxes. Since Maxwell's equations are linear, we can actually analytically solve the Riemann problem for essentially how light waves are going to propagate, and we can encode this information in the numerical flux function. So this brings me to an important point, which is we know that the continuous Vlasov equation essentially conserves an infinite number of quantities, these so-called Casimir variants. I'm not going to be so bold as to try to conserve them all, but I'd like to talk about some that we, as physicists, consider especially important, things like mass and energy. And I can ask, in the process of discretizing my system, did I retain any of these conservation properties? So let's return to the discrete weak form here. Now, because this is a Galerkin method, I can plug in for W anything I can represent with my basis. So let's try a few things. Let's try, for example, W equals 1. As long as I can represent a piecewise constant function, this is a completely fair thing to do, And what we find is that the volume term vanishes, and when we sum over cells, this surface term pairwise cancels. And it pairwise cancels because my numerical method has a property which probably sounds like a manifestly good thing. It's that the flux into one cell is equal and opposite in sign to the flux out of its neighbor cell. I'm not creating or destroying flux. And so this surface term pairwise cancels if you sum over cells, and you're left with sum over j, integral k sub j, df dt. This is density conservation, or if you prefer, multiply by mass, and you have mass conservation. So in the process of discretizing my system in space, I have still retained mass conservation. I can do the same thing plugging in for w 1/2 mv squared if I use at least piecewise quadratic basis functions. In doing so, the surface term will again vanish for this exact same reason as before, and now what I have is an equation system that tells me what the evolution of the energy, 1/2 mv squared df dt, goes like. And it actually is the discrete analog of j dot e, the exchange of energy between particles and fields. Exactly what we would hope it would be. So when you put it all together, you find that the discrete system conserves total density in the continuous time limit, and we have a discrete analog of Liouville's theorem. Phase space is still incompressible. The total energy conservation comes from how we ultimately choose to discretize Maxwell's equations. If we use central fluxes, we'll find that the total energy, particles plus fields, is conserved. And if we use upwind fluxes, we'll find that the total energy, particles plus fields, is a monotonically decaying function. Ultimately, this comes from the fact that your choice of numerical flux function in Maxwell's equations is governing what sort of errors are going to appear in your system. When you use central fluxes, you're saying all the errors in my discretization of Maxwell's equations will be dispersed, will be phase errors in the light waves. Whereas if you use upwind fluxes, you will be minimizing dispersive errors at the cost of diffusive errors. So you will have some amount of diffusion from using upwind fluxes. This brings me to perhaps the most important slide of my talk. So I've decided, for better or for worse, to condense sort of my entire thesis into a single slide. Maybe not such a great idea for my job prospects, but this is really important. It's one of the biggest discoveries we made in this algorithmic work. And that is, the Vlasov equation, these conserved quantities, are implicit to the system. You know, the Vlasov equation is just a scalar equation. It just tells you that phase space volume is conserved. In fact, it's velocity moments of the Vlasov equation that are ultimately other physical conserved quantities, mass and energy. This means that if we actually want to have these conservation properties we think numerical methods should have, we ultimately have to do the integrals in the discrete weak form exactly or to an extremely high precision. And this is unique amongst applications of DG to many equation systems. Because what you find in the literature is that often errors in the integration, so-called aliasing errors, especially when applied to fluid equation systems, they're tolerated, or even not explicitly eliminated. And you can see why, kind of looking at, for example, total mass and total momentum conservation in a fluid equation system. Because you have a nonlinearity that goes like rho u u. And you know you need an expansion of u, so you say, well, I'll just calculate an expansion of u from rho u over rho. But that is a rational function. It's a ratio of two polynomials, and I can't represent that as a polynomial. So in the end, you often tolerate these aliasing errors or do some sort of post hoc fix, some sort of filtering. And this is not just because it's an enormous amount of work to try to fix this, but also because it's very computationally favorable. It turns out you can devise cheaper schemes that still have these aliasing errors. And there's lots of work in the literature about sort of how these aliasing errors manifest. And it's actually not that uncommon to find a kind of glib remark that dealing with aliasing errors is sort of more art than science. Sometimes it matters, sometimes it doesn't. Maybe you have like a fix that works sometimes, not others. And what I'm here to say, a big discovery of ours, is that there's no amount of artistry that fixes this for the Vlasov equation. There's no amount of Michelangelo painting the Sistine Chapel, Monet and water lilies, or Van Gogh and Starry Night. You cannot tolerate aliasing errors in this system, because when you put aliasing errors into the Vlasov equation, you're manipulating physical quantities, things like mass and energy. So you say, okay, well, what does it cost to actually eliminate these errors? And this is where the famous curse of dimensionality shows up. Because if I actually wanted to integrate the nonlinear term exactly, because it's nonlinear, I require very high order quadrature. So what's to be done? Well, we can take a step back and look at what's the fundamental operation of this system. So if we look at the nonlinearity, we can think about it as actually a tensor convolution. We could write out the actual basis expansion of every term, alpha and f, and we would get a rank 3 tensor. I know I have to sum over 2 of these indices, and that would be the form of the update. Naively, this tensor is dense, and this is not any better than doing quadrature. Turns out, if we instead choose our basis expansion to be modal and orthonormal, we can now make this tensor sparse. This is quite favorable, because if the tensor is sparse, then this tensor convolution will not have that many terms in it. And so what we can do, because we're using a basis set that's polynomials, is we can actually symbolically compute what the form of the update is. And we do that. We do that with a computer algebra system, in this case Maxima. So what I'm showing here is actually an example computational kernel from our code, where I have actually written out what the output vector is from this tensor convolution. There are no loops, there's no quadrature, there's no even matrix data structure. I'm essentially encoding here what actually a forward Euler time step would look like. And so I can take just a forward Euler time step, I could do something more sophisticated, a multi-stage method. In fact, in our code, we most often use a strong stability preserving Runge-Kutta third order method. And so when you put this all together, for a reduced dimensionality here, which is 1x 2b and polynomial order 1, you see about a factor of 4 reduction in the total number of multiplications to construct an alias-free algorithm. The savings is much larger as you go to higher dimensionality, to where ultimately you can do an experimental test to determine what the computational complexity of the algorithm is. And what we find is, at worst, it scales like the number of basis functions squared. So what I'm showing here is a set of experiments changing the basis set and changing the dimensionality, and what the time it takes to update a single cell is. So here's time, and here's number of degrees of freedom, essentially number of basis functions. And I'm fitting lines to the actual, what would be the computational complexity of this system. What I'm showing here is the cost of the total update. So in 6 dimensions, it's the cost of doing 1/60 volume integral and 10 5D surface integrals. And we find that for the larger number of degrees of freedom, such as higher order basis functions in low dimensionality, or moderate polynomial order in higher dimensionality, it scales at worst like NP squared to do both the streaming term and the acceleration. And this is quite a large savings when you look at the higher dimensionality cases. I'm showing a factor of 20 for 5-dimensional simulations, and it's upwards of a factor of 50 to 100 for 60 simulations. So with my remaining time, I want to talk a little bit about how you might extend this algorithm to doing collisions. Because even though we're looking at weakly collisional and collisionless plasmas, where you expect that collisions are not necessarily dynamically important, they still contribute something to the system. In fact, you know that collisions are ultimately the source of entropy production and dissipation, and so including collisions has a sort of physical manifestation as regularizing velocity space and providing a source of dissipation. In plasmas, it can be shown that most of the collisional dynamics are essentially a Fokker-Planck equation. This is a consequence of the fact that small angle collisions dominate over large angle collisions in a plasma. And so in general, the collision operator will look something like this for some drag, coefficient, and diffusion tensor. I'm going to not do the full problem in all generality, and instead consider a simplified collision operator that still has the Fokker-Planck structure and conserves momentum and energy, at least in the continuous limit. I can go through the same arguments about how to construct a DG algorithm for this. It's going to look denser because I now have a diffusion term. And so what we have is a couple of different pieces. So the volume term has the drag component where I've only integrated by parts once, and then the diffusion component I've integrated by parts twice. We're still using a relaxed global X-Friedrichs flux for the drag term, and now, as part of the diffusion, I've changed notation here, where I have this f hat. This is because I'm using a discontinuous representation at cell interfaces. And so if I need a derivative of a discontinuous function, what am I to do? Well, our approach is to use the recovery discontinuous Galerkin method, which essentially allows one to construct a higher order representation of your solution across two cells so that you can obtain these quantities. And the basic idea is to leverage what's called weak equality, where you say two functions are weakly equal if over some interval spanned by a basis set, if you integrate over that interval, the functions are equal multiplied by that basis function. And so I denote weak equality by this integral with a dot over it. And as a pictorial representation of what recovery DG looks like, if I take my DG representation in two cells, I can construct this higher order function across the two cells based on the constraint that the recovery polynomial is weakly equal to the function in the left cell and also weakly equal to the function in the right cell. And it just turns out that in this case we choose the recovery polynomial to just be a polynomial. So second verse, same as the first. You can ask, what kind of conservation properties does the discrete scheme retain from the continuous system? So what I'm doing here now is looking at momentum. I plugged in for W, V, and I want to see if my system conserves momentum as the continuous collision operator does. The surface term, at least one of the surface terms again vanishes, and then the diffusion term, two derivatives of just V, also vanishes. This other surface term vanishes with a caveat. And the caveat is that this f hat is not necessarily 0 at the edge of velocity space. Because I'm using a grid code, I have to specify what the edge of velocity space is. So I'm essentially saying there's a maximum velocity in the system. More on this in a second. I need a couple of definitions. And so again, leveraging weak equality, I'm going to construct what are essentially the moments of the Vossov equation. Things like an analog of the density, an analog of the flow, and an analog of the energy. And it turns out, in order to conserve momentum, when I solve for u, the flow that goes into the collision operator, it must satisfy this constraint equation. So we have something that looks like rho u equals u times rho, but I'm going to have to solve for what u is, and then have this piece that comes from the edge of velocity space. And there's another constraint for total energy conservation. And it turns out this is actually a coupled system that ultimately is what allows you to solve for the two components that go into your collision operator. Now, a really important question to ask is, what practical consequence does any of this have? So I want to consider a test problem that's often used as kind of a benchmarking problem. It's a modified version of the sod shock initial condition, where you initialize a jump in density and pressure, and you let that evolve. Because we have a collision operator, you will develop shocks that have gradient scale lengths on the order of the mean free path. And so you get structure that looks like this, in the density, the velocity, and then if you'd like, in the distribution function. And so we can actually look at what our conservation looks like under a couple of different ways of computing the collision operator. And what we find is that all of this trouble actually has a very dramatic impact on your total conservation. So you can think about doing conservation, calculating u and t subject to these constraints that we've derived using weak equality and an alias-free algorithm, and then momentum and energy conservation is on the order of 10 to the minus 13. Great. But if you don't do this, if you instead naively compute u and t from what you think it might be, u would be rho u over rho, for example, your conservation is much worse. And that can have actually immediate practical consequences for real simulations. In this case, it's still pretty good, 10 to the minus 3 for the momentum, and 10 to the minus 2, maybe upwards of 10% if we ran it longer. But that's not necessarily guaranteed to be the case for more sophisticated simulations. And I want to actually, with my last couple seconds, talk about a really sophisticated application of this, which is a non-trivial problem called magnetic pumping. In plasmas, the magnetic moment, mv perp squared over the magnitude of B, is an adiabatic invariant if the magnitude of the magnetic field is varying on a time scale that's less than the cyclotron frequency. Essentially, particles are gyrating very, very fast. If the strength of the magnetic field changes slower than that gyration time scale, then the particles will respond with their actual size of their gyro orbit, and this quantity, mu, will be conserved. Now, the consequence of this is that if you drive the change in the magnetic field, you will get no change in the total energy of the system. You will essentially see that the particles adjust their local perpendicular velocity, and the result is that there's essentially no gain in the energy in the system, as there should be. But if you introduce collisions, then in the process of the particles potentially heating as the magnetic field decreases in strength, the hot particles in the perpendicular velocity will be diffused in the parallel direction. This is called pitch angle scattering. And so when you introduce collisions, you can actually have net energization. So what I'm going to do is I'm going to drive a system at a time scale that's less than the electron cyclotron frequency. And I do it with this current that's in the y direction and varies in x. And the result is a magnetic field that varies in amplitude in some sinusoidal manner. Now, if you can see the green line here, when the collision frequency is 0, you see that overall, there is actually no secular energy change. There's no heating of the plasma, as there should be. This is a strenuous test of the numerical method to say that mu is conserved by my numerics and that I don't get any energy change. But when I introduce collisions, I see that the hot particles in V are scattered into V parallel. I'm diffusing hotter particles in the perpendicular velocity into the parallel direction, and you ultimately see a net energization in the plasma. And you can compare that to theory and find that as your code can compare well to theory, provided you adjust the theory at higher collision frequency, just because of a Brzezinski calculation. And I'll just leave with this final slide about sort of this code that I work on, which is called the Jekyll framework. And yes, there is an unstable branch of the code that's not available to the public called Hyde. I'll take a couple questions, but here are some of the citations, and I'm happy to provide more information about those citations.